Nadia Peak will present, so that's very difficult, making machines that make rapid prototyping of digital fabrication and instrumentation machines. So, welcome with a warm applause. Thank you.
All right, good morning. Thanks for coming to my talk this early. Because it's this early, I figured I would start with a kind of small story about, say you wanted to make a machine. Say you wanted to make any kind of machine. What does the machine do that you want to make? Does it cut things? Does it mill things? Does it extrude things? Is it a 3D printer? Is it a laser cutter? Does it just dispense candy? And depending on what you want your machine to do, how fast does it go? Like, what is the motion that you're going to have? What is the inertia of your machine? Is it going to be very slow? Is it going to be really, really strong? Is it going to be very precise? Do you need it to move super fast? And those are all things that you might want to take into consideration when you're designing a machine that you might want to make. The next thing you might think about is, if this is a machine that fabricates or measures things, it's probably going to have to move around. So how do you move things around? With a drivetrain. So here are just some illustrations I made of drivetrains that you're probably already familiar with, like a lead screw with a lead screw nut, or a rack and pinion, or a timing belt. And each of these things have drawbacks and advantages in machine design. Like a timing belt can move very quickly, but there will be a lot of backlash in your system. A lead screw can put in a lot of force, but it might not be as fast. Rack and pinion, very cheap to prototype. Anyone with a laser cutter could make one. And so once you have your drivetrain, how are you going to hold your drivetrain in place? How are you going to make the frame for your machine? A very popular way to make 3D printers nowadays is to laser cut plywood and use a T-slot construction to hold everything together. You could use an aluminum extrusion. And how you make the frame of your machine is going to have a lot of impact on the rigidity of the machine, and therefore the inertia that your machine is going to have. If it's very heavy, it's going to be more difficult to move around. If it's very kind of loosely connected, it's going to be full of vibrations, and the resulting precision of your machine is going to be very low. Even if you have micro-stepping in your stepper motors, it doesn't really matter if you have a big floppy machine. So what are you going to do about that? And then the way that you have to restrict the motion of your machine. So say you have a lead screw that's moving things back and forth. You have to make sure that it stays in one axis, right? So you use something like a guide shaft, or maybe you use a flexure, and you restrict the motion in 1 degree of freedom, or 2 degrees of freedom, or 3 degrees of freedom, however many degrees of freedom you want. And to think about those degrees of freedom, you can think about different kinematic systems. So H-bot, delta bots, polar coordinates, those are all examples of parallel kinematic systems, right? So if you move X, it's going to affect how you move Y. And those things are dependent on each other. Whereas with serial kinematics, if I move X, then it doesn't really matter. The Y position is independent of X. So different kinematic systems result in different control systems, and how are you going to talk to all of those control systems? Did any of you guys go to Travis Goodspeed's talk yesterday about satellite control? Some of you? Yeah, so he used a stepper motor driver board that was designed for a different machine to control his satellite, right? And then he wrote a Pygame interface to look at different satellite pointings, which is pretty cool. So how are you going to control yours? Are you going to repurpose a system like that, or are you going to design something from scratch? So this is my very brief overview on if you wanted to make a machine. That's kind of the different steps and aspects that you would want to think about. So now I will go back to talking about, now that we have an overview of what machine building entails in this talk. So a long time ago, we had the Industrial Revolution, and that gave us a lot of things that were available in the color black. And using kind of mass production techniques, we were able to build things that were otherwise prohibitively expensive to build. So building a single prototype for a car, yeah, it's not something that you can really afford to do if you're only going to build one of them. But if you take advantage of an economy of scale, then, and you build lots of the same car, you can start selling them for not that much money. If you think about it, like a car being $20,000 maybe if you buy a new car. I have no idea. I've never bought a car. But like all of the systems that go into that are actually quite complex and expensive. And if you were going to prototype them one by one, that would be prohibitive. So I guess economy of scale is useful in that regard. But the way that a lot of those things were driven forward was in conjunction with kind of the militarization of the mid-20th century. And so a lot of the techniques that we developed for manufacturing and building things are really kind of closely tied to militarization. And so it's hard to extricate that kind of manufacturing and design process from jet engines, missiles, and things like that. So making tools to make tools obviously dates back to the beginning of the first tool, because you make a tool to make something else, which might need to be made with something else, right? And the first time we hooked up a tool to a computer, and with we I mean mankind, was a long time ago. So this is the first CNC milling machine, which was at MIT in the 1950s. Totally stolen idea from an independent inventor, but whatever. And yeah, that really enabled going from the precision that you would otherwise manually require with more traditional tools to be able to start using numeric readout to control things. And so then making things in an economy of scale isn't necessarily as important anymore, because the only way that you change what the object is that you're making is by changing the code, which is relatively trivial in comparison to having to change what a craftsman is able to produce. But that doesn't necessarily mean that that's the way that we're building things. These people are actually not actually building things. I think they're sorting mushrooms. This is a photo of Andreas Gursky's. But I just kind of wanted to use it as a visual reference point for maybe something that we'd be interested in departing from. Mass production kind of then results in a lot of artifacts and objects that produce desires in people that they think they want or need things. And is it really the case that you need to buy what it is that is already available? Maybe things that you need are slightly different from things that are available in the market. And so obviously, you guys like building things, because otherwise you wouldn't be at a big hackers conference. And so there are a lot of spaces like this now available, not just to do code production, but to do physical prototyping with digital fabrication equipment. So this is a fab lab in Iceland. I don't know if any of you guys know Smari, but I think Smari is from this lab. And so you have all of this equipment now that previously was kind of unaffordable or unattainable. You have 3D printers, small format milling machines that you can use to do printed circuit board production. You have vinyl cutters. There's plenty of vinyl cutters in the hall. Laser cutters, large format milling machines. So anything that you kind of think about wanting to make right now is it's kind of at your fingertips. And so I'm a grad student at MIT, and for the past, well, let's not talk about how long I've been a grad student. For the past couple of years, I've been teaching I've been teaching a class called How to Make Almost Anything. And How to Make Almost Anything just uses digital fabrication tools for students to make whatever they want. So I don't know if you guys are familiar with my advisor, Neil Gershenfeld, but he wrote this book about digital fabrication and building things. And it turns out that a result of making things with digital fabrication means that you maybe want to make more tools for digital fabrication. So how to make something that makes almost anything instead of how to make almost anything. So this is a friend of mine, Jonathan, who back in 2009 made this plywood milling machine on a larger milling machine for circuit board production. And I think it's about $400 in parts and replaces $4,000 machine that we were using to make circuit boards. And this is Ilan Moyer, also from MIT. And together with Max Lebowski, he built this MTM Multifab, which was a multi-purpose machine tool. And I don't know if you guys are familiar with the Ultimaker 3D printer, but the kinematics for that printer is inspired by the design of this machine. And so it's becoming easier and easier to build these kinds of like custom tools that you might want to use yourself. The Fab at Home project, Adrian Boyer and RepRap, making it a lot easier to have 3D printers or liquid handlers. This was a plastic snap-together version of the milling machine that Jonathan developed that you can make in a fab lab or a space that has a large format milling machine so that you can have your own circuit board production. And these are the plans for this machine. And so the cut files, the firmware, and everything is available online. And so other people started making them. This is Davide. He made one for Budapest. This is Raj and Chintan. They made 2 for Maharashtra. And then kind of iterations of this machine. So this is one. These are kind of 2 larger format ones that we built in Moscow. More iterations of more milling machines in Moscow. But there's something kind of strange about rebuilding a machine that has been designed for industrial practice, right? I don't know what your living situation maybe is like, but I have a very small apartment. And so maybe the form of these kind of desktop things is not quite correct. It's like having a desktop computer versus having a portable milling machine is somewhat, yeah, it's kind of a thought process that maybe we should reconsider. Is it important for everything to be on your desktop like that? So maybe we should. So this was So I'm going to show you in a second a video of an experiment that Ilan and I did for what if the form of digital fabrication machines was different if they were multi-purpose and smaller. This has audio.
It can happen, but didn't you? I connect with her, she didn't want to what to do.
So maybe from the video you remember from the beginning of this talk where we learned about the different parts of machine design and components that this is a parallel kinematics machine, so it has a timing belt that moves the stage around with 2 motors in kind of an H-bot configuration. There's a lead screw motor that controls the C-axis, and then there's a kinematic mount on that for the head, so it's actually a multi-purpose machine. In the video, we use it as a 3D printer, but most of the time I actually use it to make circuit boards because I find I need circuit boards way more often than I need 3D printed parts. And so it's kind of an exploration of what if digital fabrication were something that you can take everywhere, use any time, and doesn't need this like huge planning thing to happen beforehand where you design a bunch, go to a makerspace, and use equipment there. But for some reason, you know, we're not really quite there yet. This is in 2010 or so. This is milling circuit boards on my desk. I'm using a G-code interpreter running off an Arduino and like a processing sketch on an OLPC to control the milling of the circuit board. And for some reason, you know, it's not the way I constantly make boards now. It's still not is not really an enjoyable, easy process yet. So maybe something else isn't quite right about how we use digital fabrication right now. How many of you have ever used Mastercam or HSMWorks or any kind of tool pathing software? OK. So it's really terrible. Probably the reason that you never wanted to use it is because it is awful. Also, you have to run it in Windows. And after you calculate all of your tool paths, what comes out is gcode. So how many of you still write in Fortran? No one. One person. OK. How many of you still write in C? Lots of people, right? OK, so gcode is like 30 years older than C. It's really retarded. There's like 100 codes. They do random things. Each machine has to interpret gcode in a machine-specific way to be able to figure out where it's going. So you would say, I'm going to jog G0, and then you fill out coordinates, and then it has to move to those coordinates, and you have to write in your stubber motor drivers how that's going to happen. It's really quite silly. The way that you generally interface with these machines is we have super advanced file transport, like a USB stick here in my pocket. And then you have endmills that you want to put in your machine. That actually makes sense, because if you wanted to machine something, you would need endmills. But then this is the interface. This is not 20 years ago. This is a machine. It's a very expensive, fancy milling machine that I use these days. This is actually not a picture of a machine that I use, but it's the same machine. It's a horrible, horrible interface. And then after you write your toolpath, so you use this annoying software to generate a toolpath, which, if you spend enough time with it, sure, you can get proficient at it. You can get proficient at toolpathing 3D prints or whatever. But then what happens is you load it into this machine, and then you just spend time watching the machine. And the machine gets to have all the fun. And so it's just kind of, you sit there, you use a computer for a long time, and then you watch a machine. It's something seems like not very, the way that you use the tools just doesn't seem very natural. And sure, tools are getting more accessible and more affordable, which makes them more accessible. So like this is the MTM Snap grew into a company which is now out of San Francisco, and also the Form 1 3D printer, an SLA-based 3D printer, which is relatively inexpensive, both from people from my previous lab. But do we really want to perpetuate this notion of how we use digital fabrication equipment? And also, what about less ordinary machines that aren't necessarily going to make it into the general market anytime soon? So these are 4 machines that I use in my lab on a regular basis. On the top left is a CT scanner, so an X-ray machine, a kilowatt laser cutter, which you can use to cut metal, a 4-axis wire EDM, which controversially, or at least I think so, has a GPS embedded into it, because if I move it anywhere within the shop, then the Department of Homeland Security wants to know, because they think that maybe I sold it to someone who's going to make aluminum tubes for uranium enrichment, but that's a different story. And 5-axis milling machine that you can use to cut. That's quite rigid, that you can use to cut metals like titanium. And so what these 4 machines have in common, besides being over $200,000 each, is that they all run on Windows 7. It's horrible. So the way that you want to interface it, if I wanted to do anything like with the CT scanner, if I wanted to move the stage around in a way that wasn't the way that the manufacturer intended, if I wanted to look at, say, a gigapan of an X-ray instead of a rotational X-ray, you can't do it. There's no way that you can script to it. It's like an opaque box that you have no control over, because there's no way that you can communicate with it. And so what about even more playful systems? So this is a picture I took about a month ago at MIT, where a student was using 7-axis robot arm with a hot wire or with kind of a hot end to cut styrofoam. And to make the toolpath, he had written this complicated Rhino script thing that took a surface and then turned it into a toolpath, circumventing the toolpathing software that you otherwise would have to buy. And then on the left here, you can see someone holding a surge protector, right? So the reason that he's holding the surge protector is the way that he's controlling the heat of the thing that is cutting the styrofoam is by turning the surge protector off and on with his thumb. Because even though it would be trivial to write that as a software widget to be able to control the heat for that software end, the easiest thing for them to do to be able to insert themselves into the system is to put a hard wire in and turn it off and on manually. Now, that just seems completely absurd to me. So we want to have right. So instead of making more of the same machines, what about kind of different machines that you might want to be making? In the hall that way, I think, there's a ceiling kind of like this of tubes, right, in the kind of main hall area. And so this is a ceiling that one of my friends made, James, where he had to install this entire ceiling in less than a week. And so you have to hang all of these tubes at a precise distance from the ceiling. And so how are you going to make sure that they're all the correct length? Well, he made this little machine that cuts strings to the precise length that he needs. And then they're labeled so that when he shows up, the only thing he has to do is take a numbered string and hang it on the ceiling in the correct place. And you don't have to do any measurement on site or in place. And so for him, it was easier to build this kind of hacked machine than it would be for him to cut each string manually. And similarly, Alon built this 24-bit friendship loom, which is a funny project by itself, where you can design friendship bracelets on a web interface, and then it is automatically controlled with these coils, which of the threads that you lift and lower at any given point. And so to be able to make this, he needed a bunch of coils of a specific resistance. And so the easiest way for him to do that, to get those coils, was to make another machine that would wind these coils. And so, if it becomes easier to start prototyping machines to help make more machines, then maybe we would be able to have a much bigger explosion of automated control. Here's a turntable that another Machines That Make project collaborator worked on, where, OK, this is like not a very nice design, right? This is just gestural. I need a thing that does a thing. I need a turntable. And the only reason he wanted this turntable was so that the 3D display that he was working on could be photographed very stably in this time lapse. So yeah, he makes 3D displays. They're pretty cool. So how can we make all of these kind of processes easier? If you wanted to automate anything, like, do you really want to go through the stress of engineering a different system and repurposing it to what it is that you want to be making? So this is kind of how I break down all machine control systems. You have at the top of this pyramid a tool head, and the tool head is controlled by some mechanical system, which is controlled by some motors, maybe some sensors that position the motors. And they have a control system, so some kind of hardware layer that actually sends pulses to the motors. And those things are, in turn, controlled by applications and interfaces, which could be software. They could be some other kind of interface. And so if this is how we break down all of those different systems, a lot of those things are relatively straightforward, but the control system, like writing applications and software, is relatively easy in comparison to prototyping a control system. And so if making the control system is kind of the bottleneck, or at least what I saw as the bottlenecks, then what can we do to address making that kind of prototyping easier? So this is an article that my advisor, Neil, wrote back in 2004, together with Danny Cohen. Danny Cohen, the guy that said variable length namespace addressing, then we wouldn't have this whole IPv4, IPv6 problem. Anyway, the Internet of Things, the notion that everything is going to be networked in the future, assuming that we have enough space for it, and that you should be able to communicate with each node individually. And so something that I thought was an interesting thing to play with, so this is a router that I hacked a long time ago. It has like useful Linksys routers that had a serial port that you could communicate with so that you could add a little bridge so that at Mega 168 implements a serial, a slip protocol so that you can have leaf nodes hanging off this router that are addressable from the internet. So this notion of like networked leaf nodes or machine components kind of informed the way that I was going to think about making machines. And also, sometimes at work, I have to work on things that make money for our research group. So this was a big control system for curing carbon fiber airplane wings. And each node has temperature sensing and heating in it. And so that was another kind of machine network that I built to be able to communicate over this whole hardware layer, where instead of having IPv6 addresses, because it turns out no one supports that, it has a kind of address is identity is where it is in the network. And so I decided that this was going to be the way that I should also talk to the machines. So this was kind of the first control system that I built for it, a bus network. So each motor on this network has an identity, X, Y, Z. And you can address them individually by calling functions on them. So you don't have a gcode interpreter that recompiles whatever it is that you want it to do and change that into motor commands. You can write your own script that calls functions specifically on each motor on the network instead of having to go through this state space. And so it's grown since then, and so the library is now called PyGestalt. And the way that you can interface with it is you write a virtual machine. I had an argument with my friend Marco about this yesterday, where he said the only reason that you call it a virtual machine is because you think that software is all virtual and that real stuff is real. So maybe it should just be called a machine, not a virtual machine. Anyway, that was a confusing digression. Sorry. But the way that you would initialize it is for each node, you say, OK, I'm going to initialize an x-axis node. My x-axis is a lead screw. It has this pitch. It has this way of communicating with it. It has parallel kinematics with this other node. So when you call functions on it, you have to call functions on both at the same time. And that's all you have to write. You don't have to write a whole G-code interpretation layer. So if Travis had used this, he wouldn't have to had like complicatedly measured how his timing belt gearing ratios interface with each other and then write software that took that into account. It would have just done that for him. And built into the library is a way that you can add other kind of more legacy nodes. So say you got something out of the trash and you couldn't necessarily control it with the PyGestalt node library. You can still import other virtual nodes into the network. So this is a terrible photo. I'm sorry about it. But this is a gel printer that I made whistle on for Jennifer Lewis, a professor at Harvard who does functional ink printing. And so it's a pressure box, and the pressure box can like shoot out amounts of goop, and you can send it serial commands to tell it how much goop to shoot out at any given point. And so that box, with its legacy RS-232 interface, just became another node on the network that we're able to integrate into the rest of the control system. So you don't have to write something on top of another control layer that then allows everything to interface with each other. So we made another liquid handling device. It turns out that biologists spend like a huge amount of money on machines that are not technically very complicated, like moving a little bit of liquid from one well plate into another well plate. You can sell biologist machines for hundreds of thousands of dollars. I don't really understand the economics of that, but this was a collaboration with Scott and Emzo from Caltech and Will from my lab were in 3 days, we built a microliter pipetting machine using the same control system and interface. And so, not to just show you machine examples, you now no longer are necessarily confined to the interfaces that the manufacturers give you. So this is a web-based interface which combines both a tutorial for how to mill a PCB with a small format milling machine and the control system for it, so that there's like a server running that talks to both your machine and your input, generates toolpath files, and sends them to your machine online. And so this is one of the hardware layer nodes that that controls each one of these axes. So it's Atmega 328P based, which means that you can also program it through the Arduino interface, should you feel so inclined. And it has a stepper motor. It has a stepper motor controller on board, so you can use that to control different stepper motors. It conveniently has a NEMA 17 hole pattern, so if you wanted to attach it to any NEMA 17 stepper motor, that would be relatively straightforward. And so the way that you can do the control system layer for any of these machines is you just add more nodes to a network, and then you talk to it over a computer. So instead of having a monolithic control system, you have a virtual machine network. So control systems, I guess, not super exciting to everyone. So can we make the rest of the machines more modular as well? Can the rest of the mechanical part and maybe the software part also be more modular? So if we think back to the brief introduction to machine design from earlier, like what is it that you might want to be able to do? You might want to move only in one axis, maybe in 2 axes. You want 2 degrees of freedom or 3. And so we decided to build these. Kind of one degree of freedom stages, where you just move one thing back and forth, and you can communicate with that over network. You might want to add a head to that, so maybe you just want something that displays a message back and forth, or maybe you want 2 degrees of freedom, so you move 2 things back and forth, and you could add a head to this, or maybe you want to move in this direction. So like say with this machine, you could put a pen on that platform that moves up and down, slide it up against the wall, and then draw on the wall. Or if you needed 3 axes, it turns out that most of the time people want to do things in Z space as well. So if you wanted 3 axes, or you could start thinking about the ways that you could chain these kinds of machines together. So this is a 4-axis control. So you're moving something like this and like this. So maybe you can move things in this direction. So the wire EDM that I showed you a while back, that has 4-axis machine control, so that you can cut metal like a square on one side and a circle on another. And so this was a mock-up that we did for a hot wire cutter, a 4-axis hot wire cutter. So if we wanted to make airfoils for UAVs or things like that, we could make it with a machine like that. So we started prototyping this kind of modular machine network. So this is the first version that we made in Moscow in October. And then this is another version. So these are all made with HDPE. So I guess I kind of glossed over it, but the MTM snap is made with HDPE that is snap fit together, which makes it easier to prototype mechanical systems because you don't necessarily need as many fasteners, and you can build error correction into the way the plastics snap together. And so these were built kind of with the same premise that you're using plastics. But it turns out HDPE is pretty heavy if you want to have the amount of stiffness that you might require for this kind of machine. So then the latest version that we made of it is made out of bent sheet metal. So this is anodized aluminum so you can see serial kinematic system, lead screw based, guide shafts, bent aluminum frame, so that you can rapidly prototype whatever kind of machine you want. So here's last month, we built the hot wire cutter that we thought about before. Here's a video of that.
Got my A machines on the table, got my B machines in the drawer. Got my A machines on the table, got my B machines in the drawer. Got my A machines on the table, got my B machines in the drawer. Got my A machines on the table, got my B machines in the drawer. Got my A machines on the table, got my B machines in the drawer. Got my A machines on the table, got my B machines in the drawer. Got my A machines on the table, got my B machines in the drawer. Got my A machines on the table, got my B machines in the drawer. Got my machines on the table, got my machines in the drawer. Got my machines on the table, got my machines in the drawer. Got my machines on the table, got my machines in the drawer.
So that took us 22 hours to build from we had sheet metal stock and motors, and I had to solder the whole control system. And I actually did go to sleep, so it wasn't like I stayed up for 22 hours. And so kind of brings us to this possibility of, if you want to rapidly prototype, rapid prototyping machines. These are all kind of modules and parts that I've been working on to try to make that easier. So obviously, it wouldn't mean anything to you unless you could use any of it. So MTM, machines that make .cba, Center for Bits and Atoms.mit.edu, all of the firmware, all of the cut files, all of the control system, board designs and layouts are all available there if you felt like making any of them. And so yeah, that's all I wanted to show you. I wanted to thank Fabienne for inviting me here, and the Chaos Computer Club, and that's all.
Thank you very much. We have 10 minutes for question and answer. If you have any questions, please go to the microphone, and then we can start. No questions?
It's because it's very early, I understand.
It was a very good presentation, so there are no open questions anymore.
Okay, good.
There's one. Micro 3.
Hi. I notice you use a lot of numeric control machines to actually make the machines you make. Have you ever actually made anything out of raw materials without any numeric control machines, using like hand tools and things like that?
Oh yeah, absolutely.
And what's the time difference between, if you ever done something with both machine, like machine way and with hand tools? What's the
Right. Well, so I guess it kind of depends where in the prototyping process we are. So the PopFab, the suitcase fabrication machine, the first prototype that we made for that, we actually cut out of foam core. So we just cut it by hand to just kind of figure out what the system was going to look like and how it might fit in a suitcase and how it might fold. And so that was entirely done by hand. But then once you want to start building the rest of it, it kind of gets prohibitive to try to achieve that level of precision with hand tools. It's definitely possible, but my skill set is much more attuned to writing code that then is executed on a machine than necessarily making sure that I'm getting a piece of metal within 1/1000th of an inch, which is kind of required if you want to be able to move those systems precisely in that way. So I would say that it's definitely everything that you can do with numerically controlled machine tools, you can do by hand. There's nothing that's stopping you from doing it. It just might take a lot longer. And so since I have all these toys, I might as well use them. Tough life. Thanks.
Additional question?
We saw very nice movements of translatoric systems, but do you have any rotation systems? I know it's trivial, but...
Rotation-based systems? Yeah, I've built rotation-based systems before. It works fine with the library. You just import a different kinematic model for it. And so like, there are certain things that are much better to do rotationally. So at some point, we had this idea that we could cut records. And so we wanted to do a rotational system with like an amplifier with a needle to scratch. And then we were like, what are we doing? This is stupid stuff. But yeah, absolutely. Any kinematic model that you want, you should be able to use. Like the fact that things are constrained into linear systems is just kind of an arbitrary artifact of how we design things. And if you want to design things differently, then by all means, you should definitely do that.
Okay, thank you.
Micro one.
So in the videos, it seemed like the pathing was all pretty pre-scripted. Is there any ansatz, what you mentioned also, to automate the pathing and maybe in a generic way build something that can
So for example, the hot wire cutter, the way that we were doing that was James would design something in Rhino, and then I would just export things from. So he would kind of design different shapes in Rhino using Grasshopper and change kind of the dimensions of different parts, and I would import that directly into the control system. So it's not like you have any like real-time control, although in that case, because you're designing something that then is being executed by the machine. But if you wanted it to be like a pantograph or some kind of amplification, you could just use that as an input to the machine. There's nothing that's stopping you from doing that. The latency that the network has is really negligible comparison to how much time it would take you to do any kind of real-time control for it. So, yeah.
Sorry, I think that wasn't quite my question. My question was if you do more complicated shapes.
Yeah, absolutely.
Support for generating a machine tool path for all. I mean, if you plug in a machine which looks different than the last machine.
Yeah, absolutely. So one thing that I didn't show that we've been working on is kind of a generic machine tool control interface. It's called CodeCompy. You can download it from codecompy.cba.mit.edu. And as input files to kind of keep everything super generic, it takes PNGs. So a PNG is a bitmap. But if you have an extremely high resolution PNG, you can kind of take the vector path from the edges and use that as the way that you can script your toolpath. So it generates a generic kind of path description, which then you can feed into the move commands of your machine. And if you wanted to do 3-axis things, you can do it with grayscale PNGs, where the grayscale corresponds to the height layer. And so you can control, so the Gestalt controlled MTM snap machine, you can control from CodeCompy, but it can also control a lot of kind of legacy machines, like an Epilogue laser cutter. It has the toolpath, it has the file format for that built in. So if you wanted to make an arbitrary shape with a black and white PNG and then send it to an Epilogue laser cutter, you could. Which was actually a really annoying thing to add, because did you know that the engineers for Epilogue add 10,000 spaces at the end of their line, at the end of their files to do file handling well? Yeah.
Thank you.
Micro 3.
Question regarding the machines, building machines. How does the accuracy keep up? I mean, you showed a big machine building a small machine, but...
Right. OK, so that actually is not really, so it's something that seems logical, that if you would make a big machine that has a certain kind of inaccuracy, then if you made a machine with it, it would become more and more inaccurate. But actually, that's not actually the case, because depending on how you design the machine, the way that the machine fits together doesn't have to include the inaccuracies from the previous machine. So if you look at the snap lock connection of the MTM snap, it's like a buckle system, the same as you would have like on a backpack, or if you had like a strap that clicked close. And so you have different opposing forces that elastically average to make it more precise. So the more of those you kind of build into the system, you can make something arbitrarily precise depending on how you engineer the system. So even if you had, if you had something as a, if you imagine like a child that's building something out of Legos, like Legos have micron precision, right? A child does not have micron precision. So the fact that you can place the brick on top of another brick means that you can engineer precision into the system without necessarily having to have precision in the thing that built it.
Second last question from Tu.
Hello, I've got a question regarding the compatibility of PyGestalt with current workflow models for 3D printing, for example.
Yep.
So if we use Slicer to generate our G-code nowadays, yep. How compatible is it?
I mean, G-code is just a bunch of coordinates, right? So
yeah.
you can just write an interpreter that will take G-code and write, and then stream it as move functions. So I would assume, I've not written it, but I think it would be like 5 lines of code.
So you think the transition from a G-code-based workflow to PyGestalt should be relatively effortless?
Yeah, trivial.
Okay, thanks.
Last question from 3.
Yes, so I checked out the website of PyGestalt, and it says that it will be published open source in November 2013, but
yeah, that's a little bit of a problem, but it's on GitHub. If you go to the MTM website instead of the PyGestalt website, there should be a link to the GitHub for it.
Thank you.
Sorry about that. I'll fix that.
Thank you very much. Applause.